Welcome to the deep dive. So today we're seeing large language models pretty much everywhere, right? Helping with emails, summaries, even creative stuff. But, as these AI tools get deeper into our lives, particularly in really critical fields, there's this huge question that keeps coming up. Can we actually trust them?
That's a big one.
Yeah, I mean, it's not just about being right most of the time. We need them to grasp and maybe more importantly, tell us when they might not know or when they're just, well, guessing.
Right, that ability to communicate uncertainty, it's fundamental.
Absolutely. For building AI that's dependable, responsible. So today we're going to dig into some really fascinating research tackling exactly this. Our deep dive is centered on a paper called Beyond Binary Rewards, training LMs to reason about their uncertainty.
Yep, this work comes out of MIT, Massachusetts Institute of Technology.
Yeah.
And it really looks into some advanced new methods to make these language models more reliable. Specifically, it's about teaching them how to quantify their own uncertainty, moving past that simple right or wrong way of thinking.
Okay, so our mission here for you, our listener, is really to unpack the methods and the findings in this paper. We'll break down this new approach they call RLCR reinforcement learning with calibration rewards. We want you to understand how it works, why it seems to be so good at handling AI overconfidence, and, how it could lead to AI we can depend on more.
Sounds good.
All right, let's kick off with something we kind of know works well. Language models trained with reinforcement learning, particularly when they generate those reasoning chains, thinking step by step.
Chain of thought.
Right, chain of thought. It really seems to boost how well they do on tough question answering tasks. It's a definite leap forward. But there's a catch, isn't there? A sort of hidden downside to this success. What happens when the model thinks it's got the answer, but it's really just guessing intelligently?
Well, that's exactly the critical limitation the paper points out. In the standard ways we do reinforcement learning for these tasks, often called RLVR reinforcement learning with verifiable rewards. The issue is how they get rewarded during training. RLVR usually relies on a really simple binary correctness reward.
Binary meaning?
Meaning the model gets a 1 if the final answer is correct, no if it's wrong. That's it. No middle ground, no way to express, like, I'm only 50-50 on this one.
Ah, okay. And that's the heart of the problem then, because this binary system, it rewards models equally whether they are confidently correct or merely guessing.
Exactly. If you luck into the right answer, you get the same reward as if you knew it cold.
Right.
And this has an unintended side effect, as the paper puts it. It basically incentivizes what they call overconfident guessing. The model learns, hey, always sound confident, even if I'm not sure. And this degrades calibration.
Calibration. That's how well its confidence matches its actual accuracy, right?
Right. Precisely. If it says 90% confident, it should be right 90% of the time.
Yeah.
When calibration degrades, maybe it says 90%, but it's only right, say, half the time. Big trust issue. And this also increases the rate at which LMs generate incorrect responses or, hallucinate more. Studies back this up. Models can get more overconfident after this kind of RL training.
Wow. So thinking about the real world, that's a major bottleneck. Imagine using these in, say, healthcare. You definitely don't want an AI confidently giving a diagnosis based on a guess.
Or in law, yeah.
Yeah.
You need to find the right case law, but also flag when it's unsure about how a precedent applies.
So in these high-stakes areas, accuracy isn't enough. Models need that ability to communicate uncertainty, to know when to say, I don't know, or I'm not sure.
That's the challenge.
Which leads us straight to the paper's proposed solution, RLCR, reinforcement learning with calibration rewards. How does this start to address that overconfidence problem?
Okay, so the key difference with RLCR is a tweak during training. The LMs are prompted to generate both their answer, their prediction, and a numerical confidence estimate. This happens right after their reasoning process, their chain of thought. So it outputs something like, the answer is X and I am Y% confident.
Okay, so it's explicitly stating its confidence level.
Yes, and the really clever bit is the reward function. RLCR's reward doesn't just look at correctness, it augments a binary correctness score with a Brier score.
Brier score. That's probably new to a lot of listeners. What is that and what does it add here?
So think of the Brier score as a way to measure how good the confidence prediction was. It's what's called a proper scoring rule. Essentially, these rules incentivize honesty. The score is best minimized, actually, when the stated confidence Q truly matches the real probability of the answer being correct.
I see. So it penalizes being overconfident and wrong, but also being underconfident even when right.
That's right. It encourages the model's confidence level to be, well, calibrated. It rewards accuracy and self-assessment. So the full RLCR reward combines both. RLCR correctness, near the one, minus the Brier penalty. Basically says, be right and be honest about how sure you are.
That makes sense. Is there a solid theoretical underpinning for this? Does it mathematically guarantee it solves the problem, or are there maybe hidden trade-offs?
Well, the paper offers a proof, arguing that RLCR provably incentivizes both accuracy and calibration. It's quite strong. It means the map is set up so the highest reward comes when the LM gives the most likely answer and a perfectly calibrated probability estimate for that answer. And importantly, this holds for specific types of scoring rules, like the Brier score, which are bounded and proper. They also note that other common methods, like using log likelihood loss directly for this, don't have this nice property. Log likelihood can sometimes, maybe counterintuitively, incentivize the model to output a wrong answer very confidently just because it assigns a high probability somewhere, even if it's the wrong spot. So the choice of the Brier score here seems quite deliberate and important.
Okay, so the theory sounds solid, promising on paper, but how does RLCR actually perform in practice? Let's look at the experiments. How did it do on in-domain tasks similar to its training data?
The results on Hotpot QA, which is a pretty complex question-answering dataset, were really positive. RLCR matches the task accuracy of RLVR, so it gets the right answers just as often.
No trade-off on accuracy, then. That's good.
Right. But the crucial part is it substantially improves calibration. The expected calibration error, ECE, which measures that gap between confidence and accuracy, it dropped dramatically. From 0.37, which is quite poorly calibrated, down to 0.03, which is remarkably good calibration.
Wow, 0.37 down to 0.03. That's a huge improvement.
It really is.
Yeah.
It means when the RLCR model says it's, say, 80% sure, it's actually right about 80% of the time. And they saw similar strong improvements on math data sets, too. ECE went from 0.26 down to 0.10. So it seems consistent across different kinds of problems.
That's impressive for tasks it's familiar with. But the real acid test often is generalization, right? How does it handle out-of-domain task stuff it hasn't really seen before?
Yeah.
That's usually where things get tricky.
And this is where RLCR really shines, actually. The standard RLVR approach. It actually got worse on calibration when faced with out-of-distribution data compared to the base model before RL training. It became more overconfident on unfamiliar ground.
Oh, interesting. So standard RL makes it less trustworthy when it goes outside its comfort zone.
It seems that way. But RLCR, in contrast, substantially improves calibration, even on these out-of-distribution tasks. It did better than the base models, better than other methods they compared against. And it managed this while maintaining or slightly improving on task accuracy. So it generalizes much better in terms of trustworthiness.
Why, though? Does the paper suggest why RLCR generalizes so much better? What's the thinking there?
They offer three main hypotheses. First, they think that making the model explicitly reason about uncertainty and chain of thought helps it reflect on confidence more deeply. It's not just finding an answer. It's thinking about its certainty level.
Okay, so the process matters.
Second, the training dynamics of RL itself. Because the learning target is always shifting slightly based on the rewards, it creates non-stationarity. This forces the model to learn more robustly, rather than just memorizing patterns from the training data. It helps generalization.
Like learning to hit a moving target makes you a better shot overall.
Kind of, yeah. And the third idea is about shared representations. The parts of the model figuring out the answer and the parts estimating confidence are all linked together in the same network. So the calibration process can tap into the same internal knowledge used for solving the problem. This makes the whole system more coherent.
Integrated learning, essentially.
Exactly. And just quickly on the data sets they use, that Hotpot QA modified one is neat. They deliberately removed relevant info to force the model to deal with uncertainty. And the math data set, Big Math, used numerical answers for easy checking. They also tried a variant, SFT plus RLCR for math, which got great calibration but slightly worse generalization accuracy, possibly due to catastrophic forgetting. Learning the new calibration task maybe interfered a bit with older knowledge.
Okay, this is all very interesting research-wise, but let's bring it back to practical use. How can we actually use these verbalized confidence scores the RLCR model produces, say, at test time, when we're deploying the model?
Yeah, the paper looks into test time scaling methods. And what's cool is that this verbalized confidence acts as an effective proxy reward. The model tells us how much we should trust its own output.
So we can use that signal. How?
Well, one clear application is when you get multiple answers from the model, maybe by asking it the same question several times. They found a confidence-weighted majority vote works best. Instead of just taking the most common answer, vanilla majority vote, or the answer with the single highest confidence score, max confidence, you weigh each answer's vote by its stated confidence.
Like giving more weight to the answers the model felt more sure about.
Exactly. And that method outperforms both vanilla majority voting and max confidence in their tests.
That's a smart way to use the confidence. Can we go further? Can we actually improve the confidence estimates themselves? Make them even more reliable?
Yes, they explored that too. One technique is ensembling what they call K-analysis cutees. Basically, for one given answer, you ask the model to generate multiple chains of thought about its uncertainty.
So get several opinions from the model on its own confidence for the same answer.
Right. And then you average those confidence estimates. They found this consistently decreases the Brier score, which means calibration gets even better, more stable, more reliable confidence.
Okay, that leads to a deeper question I was wondering about. Is it just having that number, the confidence score, that matters, or is the process of reasoning about uncertainty, that chain of thought, also playing a key role in improving calibration?
Great question. They tried to tease this apart with an experiment. They trained two classifiers. One, a baseline classifier, looked at outputs from a standard RLVR model, no uncertainty reasoning. The other, an analysis classifier, looked at RLCR outputs, but they removed the final numerical confidence score, so it only saw the uncertainty reasoning chain.
Okay, so comparing a model that didn't think about uncertainty versus one that did, but hiding the final score from the second one, what happened?
The result was pretty telling. Analysis classifiers outperform baselines at smaller sizes. This suggests that, especially for smaller models with less capacity, the explicit uncertainty cotee, the act of thinking about uncertainty, is essential for better calibration.
Interesting. So the reasoning itself helps, especially when the model isn't huge.
Yes, though for the larger 7B model they tested, the performance was similar between the two classifiers. This might mean larger models can implicitly figure out confidence just by looking at the solution without needing that explicit uncertainty reasoning spelled out.
Okay, one last area, consistency. When the model gives these confidence scores, how stable are they? Does it give the same confidence for the same answer repeatedly?
They looked at two kinds. First, inter-solution coherence. How consistent is the confidence if you generate multiple uncertainty analyses for the same answer? They found mostly low variability. So the estimates are generally stable for a given answer. If you think 70%, it usually sticks around 70%. That's good.
And the other kind?
Inter-solution consistency. This is for tasks where answers are mutually exclusive, like multiple choice. Only one can be right. Ideally, the confidence scores across all possible answers should add up to 1 or 100%. On in-distribution data, RLCR's confidence sums did cluster tightly around 1. This shows a well-calibrated belief distribution.
So it understands the probabilities should sum up properly.
Mostly, yes. On the harder out-of-distribution data, some overconfidence still crept and the sum might go above 1. But even then, RLCR remained significantly closer to the ideal sum of 1 compared to the other methods. It maintained better overall coherence.
Okay, so wrapping this up, this deep dive really shows RLCR is a significant move forward, wouldn't you say? Integrating these proper scoring rules, like the Brier score, into RL seems key. It trains models not just to answer, but to think about and state their uncertainty.
Absolutely. The benefits seem clear. Improved accuracy and calibration, especially when generalizing to new situations where other methods struggle. Plus, better self-consistency in the confidence estimates themselves. It points towards models that aren't just smart, but also more transparent and reliable about their own limits.
Which leaves us with a thought for you, the listener, to mull over. What does it really mean for us, for society, when an AI can not only give an answer, but also tell us with some measured certainty how confident it is? What new doors open when our AI systems can share their doubts just as clearly as they share their conclusions?